Good morning, good afternoon, everybody. Right on cue, my builder has just got his tools out and started creating noise. I hope you can't hear that too badly. So it's John Douglas. I'm just going to give it another minute or so to let some more people sign into this, and then we'll get started. Okay, so good afternoon, everybody. I think most of the people who are going to join have probably joined already now, so I'm going to get started. Thank you to everyone for taking an hour out of their time to listen to this webinar on addressing the challenges to sustainable operation of gas turbines. My name is John Douglas. I've got an introduction slide coming up. I'm going to talk through, obviously this is a very big subject area. I'll talk briefly about some of the work that we at Fraser-Nash have been doing in this very big subject area, and I obviously can't cover all of what we're doing and all of what happens in this area, but hopefully you're going to find what's presented today of interest. So next slide. Hopefully, Laurie, you can see that. I don't know if you want to give us a brief introduction to yourself before we get started.
Yeah, thanks, John. Yeah, so I'm Laurie Brooking, and yeah, my interest in high temperature materials sort of started with my PhD at Cranfield University, where I was looking primarily at degradation in gas turbine materials, gas turbine blade materials, so single crystal superalloys and superalloys. And after kind of being in the research environment there, I then moved over to consultancy and started at Fraser-Nash, and sort of since then have been continuing to work in largely high temperature materials and asset integrity, so looking at how we can help our clients to improve the integrity of their assets and longevity and get the best cost benefits. So yeah, that's me.
Thanks very much, Laurie. So I guess my interest started very similarly to Laurie's with a PhD in gas turbine materials as well. I'm a mechanical engineer, but I was looking at single crystal alloys from a creep fatigue perspective rather than from a degradation, oxidation type point of view. And over the years, I've been with Fraser-Nash for over 17 years now in various roles. More recently, on the commercial side, looking after the account for turbines, and I've recently set up the Rotating Machinery Centre, which I'll talk a little bit more about as we go through the slides. In terms of the presentation today, hopefully the content slide has come up. There's an opportunity, obviously, to advertise Fraser-Nash. So a quick slide on Fraser-Nash without making it too much of an advertisement, but really just a brief on who we are and what we look like today. Moving on from that, my little corner of Fraser-Nash, which is the Rotating Machinery Centre, and some of the work that we're doing within that capability area. And really, the presentation today is about the use of physics-based models for asset management, for want of a better word. Digital is one of those words that's used quite a lot at the moment. What we're doing does fit within the description of digital one way or another. So we call it digital assets. There's a lot of talk out there about data and analytics, and there is a place for that, but with complex machinery like this, we find that the use of physics-based methods or mechanical engineering gives us a better result in some instances. And so there's various parts of that physics. I'll get into some of the detail on that, but really, once I've given an overview of that approach, it's over to Laurie to a presentation on what he's looking at in terms of corrosion fatigue interactions in single crystal alloys, a very particular corner of those physics models. The next slide. Oops, I think I've gone to. So a little bit about Fraser-Nash. I've been here for 17 years. We were less than 100 people when I joined. We've had quite a growth trajectory. We've moved out of the UK and we're now in Australia as well. So we have a significant number of offices in the UK. We've got 4 offices in Australia. I hope I'm not misrepresenting the Australia offices in terms of they've been there around about 10 years, and I don't know if it's over 100 people in those offices now, or if it's getting closer to 200 people, but it's that sort of order of magnitude. In total, we've got 900-ish permanent staff in our offices in the UK and in Australia. We have a number of other people positioned around the globe in America and Europe on the site with clients doing some interesting work as well. If we haven't got an expert within the company that can help, then we have access to a network of over 3,000 other associates who we can call on for expertise. So we have quite a broad network, very, very broad capability across those 3,000 to 4,000 people. And if we still can't find someone that can help with a problem, then we have very strong collaborations with the universities. The vast majority, well, a large proportion of the people at Fraser-Nash have done some informed postdoctoral study, or postgraduate study, either masters, PhDs, postdoctoral, and so very strong links to academia. And if we can't solve it, if our associates can't solve it, then we can call on those collaborations to get experts in to help with whatever problems. We're obviously getting something right. A lot of our customers keep coming back for more and more help, and that's great. There's various reasons for that, but I think the biggest reason for that is the fact that we don't just put people on site and sell people for man hours, if you like. We like to own our customers' problems, and we like to provide solutions to those problems. And I think it's that approach which gives us an edge in the marketplace. So that's I guess that's the advertisement over for Fraser-Nash. If you want to find out more, you can call me, or you can get in touch via the website. We might be able to help you. Moving on, my little corner of Fraser-Nash is the Rotating Machinery Centre. Recently set up just before Christmas, and we've launched a part of the website which is fnc.co.uk /RMC. And broadly speaking, that gives you a brief overview of some of the skill sets that we've got in the rotating machinery field. The vast majority of it is around gas turbines, steam turbines, pumps, that type of stuff. But actually, we do a lot of work on other rotating machinery, including energy storage devices and rockets and various other gadgets. So we've got a vast experience. We even do stuff on fans for kitchen appliances and that type of stuff. So we've got a broad experience there. And if you go to the website, you'll find out. Broadly speaking, we've got 3 service areas. Machinery design. A lot of our engineers have had careers at original equipment manufacturing companies and have brought a lot of that design experience with them. Others have spent time on site with those customers and gained a lot of experience in terms of design. And so we whether it's a component design for a blade or a disc or a combustor, or whether it's a full system or a stage on a turbine, we can pick up that kind of work. And depending on the type of machine that we're looking at, we can actually design a full machine and give you a set of drawings, and we can work with you to get that manufactured. So we have a significant machinery design capability there, and some of that is outlined on the website. The next part of our service capability there is digital assets, and that's what we're going to be talking about today. So I won't go into too much detail here. And then engineering services. If we've got a broad range of services, we've got a lot of engineers doing a lot of different things in a lot of different teams. If it's not covered by machinery design or digital assets, then there are a list of services there. And there's a brief list here which covers thermodynamic performance, rotor dynamics, materials, that type of stuff. And before we get into the talk on digital assets and then into Laurie's presentation, just a quick example of a service area under the engineering services. So hopefully the slide is refreshed. There's a picture there of a gas cloud within a gas turbine enclosure. Our team of fluids engineers have been working with customers, been working with health and safety laboratories to develop standards around ATEX and DESIR in terms of ventilation of enclosures. And a lot of that work over the last 20 years has been focused primarily on methane gas clouds. Where do they form? How do they form? Are they ventilated? And if they're not ventilated, where do we need to put sensors and that type of work? Like I say, the team have been working on this for a very long time. They've developed some very efficient fluid dynamics methods which cover the basics of how to get that done and how to get that done really quickly, really efficiently. So if you have that kind of problem, you really should be talking to our team. They're central to the development of these standards and understand how to solve those problems and understand how to get you certified in those sorts of problems. More recently, that team have been working on how those standards can be modified, how they're affected by the introduction of hydrogen, and whether that's hydrogen at 1% or 100% and anything in between. Those simulations are underway, and we are working with various partners to develop that standard and to actually look at installations within European facilities at the moment. So it's a little bit left field, but that's just one of the services that we can offer. It's worth having a look at the website to see which other services we offer. It's still under development, so not everything that we offer is on there. And if you want to find out more, again, please call me or get in touch via the website. Getting into what are we doing on the asset side? I guess a lot of people on the call will be aware that the OEMs, power stations, owners, operators have got a lot of telemetry on gas turbines, and whether that's a small unit pumping gas along an oil and gas pipeline, or whether that's a large power station. For a long time, a lot of data has been coming off there for the purpose of vibration monitoring, performance monitoring. We've figured out over the last 5 or 10 years how to make best use of that data in terms of understanding what's happening with the machine. And even just at a simple level, am I running at full load steady state, or am I running at part load 50%? We've got some real-time algorithms which look at the data, understand what level the machine's operating at, and then we've got lots of physics models, we've got lots of algorithms which will get into the detail of what's happening with metal temperature and metal stress within the components that are of interest. So if you're running at full load steady state, you're expecting various failure modes within blades or discs or nozzles. We're monitoring the stresses, we're monitoring the temperatures in those components real time, and we're able to understand from that how much damage is accumulating within those components. And you can integrate that throughout the life of that turbine. We do that with various physics-based approaches, including creep, fatigue, corrosion, and oxidation. My interests are around creep, fatigue. Laurie is very interested in the corrosion and oxidation end of things. But we bring all of those models together to understand the condition of your machine at any given point in time. And there's various advantages or various opportunities coming out of that. Not least flexible operation. So can I run my machine at 50% power for longer than the usual maintenance window? The answer is yes, you can, generally speaking. Part load power is generally less damaging than full load steady state or than the design case, but not always, and that's where the physics comes in. So data analytics on its own can't tell you when you're going to bake the back end of a gas turbine, for instance. And so running at part load, generally it's less damaging, but there are instances where you will cause more damage by running at reduced load. And it's the physics models that really get into the nitty-gritty of that tell you why and when those things are happening. So flexible operation, can I extend the life? Well, the physics will tell me whether I can or not. What if I want to run at power boost. What if I want to do 120% for a couple of hours a month? What does that do to my maintenance window? What does that do to the damage within the engine? And that's where the value of these sorts of algorithms come in. Can I optimize part placement to recover part performance of the gas turbine? Yeah, you can. So we can monitor the engine. We can use the physics to understand when you might want to do a wash on the compressor, or when you might need to replace some nozzles which have started to build up product on them, or durability issues. So when to replace parts, when's a good time to replace parts, that sort of stuff falls out of the physics. And then maintenance deferring. I know my engine is coming up for maintenance within the next 3 months, but actually I want to run it for 6 months. What was my previous use case done to the condition of those parts, and can I defer my maintenance while I get through this busy period for the next 6 months, and those sorts of questions. And that's the kind of stuff that we're working with power stations, that we're working with OEMs to solve, and using these methods to actually do. So a little bit more detail on without getting into the physics, a little bit more detail on the technical approach. We start simple and we build from there. So we've got some very, very simple models that tell you about what's going on in the physics of creep, fatigue, corrosion, oxidation. There's no point in us developing highly complex models for your engine on all corners of that. The best approach is to start with simple models and then start looking at the results that are coming off that, and we'll find out very quickly whether your engines are creep dominated, fatigue dominated, or if they've got oxidation and corrosion problems. And from that, we can then start to build in more and more detail on the physics and take it from there. There's no point in building a highly complex fatigue model if you've got a creep dominated machine. That's the first point. I guess the next point is that this is all about risk. We obviously need to understand what's going on with the creep and the fatigue for various reasons, but actually the sensors, the data that's coming off the sensors isn't 100% accurate. What's going on with thermocouple drift? Is that thermocouple accurate? Is it even working? Those sorts of questions come into your risk-based model. What about my LIFE model, my creep model? If I'm starting with a basic creep model, then there's obviously a lot less certainty on the accuracy of that model versus a more bespoke model which is being developed very, very neatly for your application. And so understanding the uncertainty, understanding the risk that comes with that uncertainty is a big part of what we're doing. And all of what we're doing here sits within a probabilistic wrapper. Those methods have been developed from Monte Carlo simulations of graphite cores on nuclear reactors. So we're pretty confident that those methods work, and we're pretty confident with the answers that come out of that. And I guess the last point on this slide really is about the fact that we're not hungry for more and more data. It's obviously always quite nice to have more data, but the more data you have, the bigger the problem you've got of processing it. There's a lot of machinery out there with sensors. What we try and do is make best use of that sensor data without actually needing to go in and refit new sensors and new telemetry. We just try and make use of what we got. Occasionally we come into a situation where we just don't have enough data, and it is sensible to put more sensors where we need them. But most of the time we get away with just the sensor data that exists. So it's not a big expensive job to refit your fleet. And then just turning some of that into a picture quickly. On the left hand side, we've got the data platform. On the right hand side, we've got a risk-based decision making tool, and in between we've got our physics-based tool set. Just to, on the first level, we've got some very simple models. We will implement them very quickly, very cheaply, to start producing results. And once we start to get results from that kind of approach, that's when we can start to think about, do we need a creep fatigue interaction model? Do we need a more complex corrosion or oxidation model? And from that, do we then need to get into the various specialist models that can be developed on a need-must basis. Hopefully that's given you quite a nice overview of our approach to managing your assets using sort of digital techniques coupled with physics-based approaches. I can't talk in detail about all of that. I'm not going to talk in detail about all of that. I think at this stage, really, that's a little bit, that's enough of an understanding to understand our approach. I think I'm just going to hand over to Laurie now, so that he can talk a little bit about his corrosion fatigue interactions and what he's seeing on single crystal alloys.
Great. So hello everyone. Yeah, my name is Laurie Brooking, and I'll be taking a quick look at corrosion fatigue interactions in single crystal superalloys. So this is a common issue, and it's seen both in industrial and aerospace gas turbines, and it's a cracking morphology often similar to fatigue, that's observed typically in hot gas path components, earlier and sooner than predicted. So we'll be talking about what causes this issue, how do these cracks propagate, and how we can look to predict and mitigate against this problem. So on just at the right here of the bullet points, you can see there's a couple of images of micrographs of CMSX4 single crystal superalloy, if you're not familiar. So I was just going to kind of explain what is a single crystal superalloy, why they're different to a lot of other alloys. So you can see we've got that cuboidal type microstructure. It's gamma prime microstructure it's referred to as, and the gamma prime is the kind of the cuboidal feature, the square feature there, and the matrix is the bit in between those cuboidal features. So they're both face-centered cubic, and the gamma prime is an L12 ordered face-centered cubic. And just next to that, the really high mag 5 nanometer image is showing you the interface between that gamma and the gamma prime. So really this is what makes these materials a bit special. So whilst you've got two phases, because the unit cell size is so comparable, we actually don't really see a phase boundary. You can see the lattice coherence is really very good in these materials. Certainly at this temperature, obviously things change around a bit with different temperatures, but we don't really have a grain boundary, hence why we call it a single crystal superalloy. And that comes with numerous advantages for high temperature material properties, creep, fatigue, things like that. Along the bottom, I've got some images of what typical corrosion fatigue damage looks like. So what we're talking about in this presentation, the types of damages we would see. So the image on the bottom left there is of an industrial gas turbine, and we can see a corrosion damage on the platform where the arrows are pointing to, and actually bits of material have broken off there. The middle image is under corrosion platform, and again this is quite typical of what we would see. So it's a highly stressed area of the blade, but actually lower temperatures than a lot of other parts of the blade, or some other parts of the blade. But we see colonies of cracks propagating through the platform, through the root region, that highly stressed region there. And then the image on the bottom right is actually an image of what can happen if this goes undetected. Obviously this happens a lot sooner, as I sort of said, than expected in many cases. And if it's not noticed, the image on the right there is some blades which have been ejected out the back of an aircraft engine actually upon takeoff. So certainly not something that you want to be happening. A bit of background then into why this is happening. And we believe the cracking occurs as a result of simultaneous deposit-induced hot corrosion. I'll talk a bit more about what that is in a bit, combined with loading or stress. And the cracking can occur as under static loads as well as fatigue cycling. So it's kind of a bit of a stress corrosion cracking type mechanism, similar to what we would see, in aqueous stress corrosion cracking at obviously much lower temperatures typically. And I think a very, very good question is, why has this mechanism become prevalent in recent gas turbine designs? And I think there's a couple of reasons for that. The first is increases in turbine efficiencies, driving up operating temperatures due to your Carnot cycle, and we see the extended effect of hot corrosion. So really we're pushing the boundaries and trying to improve efficiencies of these turbines, or running some different fuels, hydrogen, etc., which might need us to look at running at higher temperatures, and that can really extend the effects of
hot corrosion into areas where we wouldn't typically see it. The second use is sort of related. So because, again, we want to achieve higher temperatures to improve efficiencies, we're looking at using materials which have higher gamma prime fractions, due to they've got higher gamma prime fractions in order to achieve better high temperature properties, so better creep properties and things like that. But by increasing the gamma prime fraction, we actually reduce the refractory element concentration or weight percentage, and those refractory elements are really very good for building up protective oxides. So we typically see with a lot of the really good high temperature superalloys, they're a bit worse, particularly at lower temperature corrosion. So there's a bit of a trade-off there, and that's another reason I think we're seeing this mechanism become more of an issue as we use those real high temperature, high gamma prime fraction superalloys. So I was just going to introduce high temperature deposit induced corrosion, or hot corrosion, because it's not necessarily that well known about. So it's typically defined by two mechanisms: low temperature or type 2 hot corrosion, and high temperature or type 1 hot corrosion. You can see there on the figure on the right, we've got a fairly linear relationship between temperature and oxidation rate. However, you have these two humps of accelerated damage for type 2 and type 1, with type 2 occurring at slightly lower temperature. And the reason we get these two humps is largely due to chemistry. So hot corrosion occurs as a result of corrosive species forming a liquid melt or eutectic on the surface of the blade, and it typically is forming due to gaseous conditions and also the deposition of those species. So depending on your alloy composition, your coating composition, your deposit composition, you can see the temperature of these mechanisms move around. And actually, historically, that graph there on the right is often thought of as a kind of baseline, but I think in reality the chemistry is quite a lot more complex, and we see a bit more of a probably complex picture in reality. So it's typically thought that hot corrosion is electrochemical, so that liquid deposit or liquid mixture forming on the blade is an ion transport, and is enabling acidic dissolution to happen kind of localized locations and cause this cracking. Just a general note on alloys and how they tend to respond to this mechanism. Generally speaking, chromia forming alloys, so alloys which form a chromia oxide, are more resistant to type 2 and lower temperature oxidation and corrosion, and your alumina forming alloys are more protected for type 1 and higher temperature oxidation and corrosion. I also think it's sometimes debated a little bit as to whether or not hot corrosion reactions are deposit regulated, or whether they're regulated by gaseous composition or partial pressure of SOx or SO3. And I suppose in my view, again, I think there's several competing mechanisms, and it's quite a complex picture. However, I suppose of note, in industrial gas turbines, you often have filtration, which is limiting the amount of solid salt or deposit species, or species which can be injected through the engine and deposited. So I think in a lot of the time we may see more of a kind of a factor of your gaseous concentration in terms of limiting your hot corrosion. However, in aerospace engines we don't have that same filtration. So I think a lot of the time composition and deposit composition can play a bigger part in aerospace applications. So again, I think it can vary a little bit, and there's quite a lot of complex chemistry going on as well. So if we take a look then at some experimental test results here, these are a couple of images of statically loaded specimens. So there's no cycling here. These are cracks which have been generated, in line with kind of stress corrosion cracking rather than fatigue. And what we see is multiple initiation sites. So the top image there is of a plain cylindrical specimen, again statically loaded at quite high stress there, 900 megapascals. But we see multiple cracks initiate and propagate. Obviously it's very much dependent on the corrosion. So if you take away that corrosion, you obviously don't expect these materials to to initiate and propagate cracks at these temperatures. It really is corrosion driven. The lower image is showing something similar, although it's an optical image rather than a scanning electron microscope image. And that's showing a similar thing on a C-ring at a slightly lower stress there, 500 megapascals. But we can see again multiple crack initiation sites and environmental kind of marking as well going on, so showing the sort of significance of the environment to this crack propagation. If we have a look at a few cross-sectional images now then, we can start to see how this mechanism is interacting a bit more with the microstructure. So image A there up on the top left is showing what looks to be a bit like a corrosion pit, and we've got a crack which is initiated and propagated out the bottom of that pit. We obviously can't tell what came first, the pit or the crack, but we also see the corrosion interacting preferentially with the gamma prime, and this is kind of backed up by the following images. So we can see really at the crack tip there in image B, again, it's interacting with the gamma prime, propagating on orthogonal Q planes through the material, and even some bridging through the gamma. So the gamma prime is typically the strengthening phase or precipitate. So preferentially oxidizing that is obviously locally weakening the material and enabling this crack propagation. If we have a look then, what we've got here are PD plots. So these represent the crack growth or propagation rate throughout the test. So the way we do this, and again, it's quite a common technique that's used in fatigue, less so in stress corrosion cracking, and again, less so at high temperature with deposit-induced corrosion. But it's quite a useful method for us to actually look in a bit more detail at what's going on. So what we do is we pass a large current through the specimen, and we have a couple of probes either side of where we expect cracking to occur. And as that crack propagates and we lose specimen cross-sectional area, we see an increase in potential drop or resistance, which we can measure, and that corresponds to our crack size. So there's two tests here. They have comparable test conditions, other than they're using different salts deposits, so a different composition of the salts. So the one on the left is sodium potassium sulfate based salt. We can see an incubation period, so the crack hasn't started straight away, but then it initiates and it's kind of continuing on then at a very linear rate, not really showing much correlation to the crack size as we would expect to see with fatigue, fairly linear rate trundling along. If we have a look at the chloride salt, we see something similar, except we've not got that incubation time. We do have an overall linear growth rate. There's a little bit of jumping we can perhaps see going on there. But I think the key thing to note here is that with these two salts, we see a very different rate of propagation. So obviously these aren't calibrated. We've just got potential difference here, but it does correspond to the crack size. So we can see that the rate of increase of potential drop, or the rate at which potential drop's increasing, is twice as high for sea salts. So that chloride-based salt, at these temperatures on these alloys. So it's kind of highlighting the significance of what the deposit is actually made of, or what the composition of the deposit is, for this mechanism. So starting to introduce fatigue into the equation then. So now we've got stress cycling going on. This is quite a simplistic view of how corrosion, or this type of corrosion, affects fatigue life of these alloys. And again, it doesn't tell the whole story, but it does start to help us unpick a little bit what's going on. So we've got three curves on this stress cycles to failure graph, so an SN curve. The first two or the square and the triangle, are 5 microgram fluxes, so that's the rate of deposition of our corrosive species, and the circle is 1.2 microgram centimeter squared per hour rate of flux deposition. So if we compare the two 5 microgram results to start with, one is a 1 second dwell, so this is a trapezoidal test, so we're ramping up the stress and we're holding it. That dwell time represents holding the stress at a maximum value, and then we're ramping it back down. So we've got a 1 second dwell and a 60 second dwell. So the 60 second dwell test, the triangle, contains or has a lot more corrosion occurring per cycle than the 1 second dwell. So we can see more corrosion in that case, worse fatigue life. Fairly simple story. And if we compare the two 1 second dwell tests, so the square and the circle. Again, the square has a higher flux, so more corrosion than the circle, and we can see again that drop in fatigue life corresponding to that increased amount of corrosion. So that's all makes sense. But again, this is quite a simplistic view, so we'll start to dig into a bit more what's going on, because I don't think SN curves are a great way to look at what's going on. So what we've got here then is again using that potential drop technique, but this time on fatigue specimens, 550 degrees C, and these are notched fatigue specimens. We've got some plots of the crack propagation, so showing how that crack depth is varying over both cycle and time. This sort of starts to give us a bit more information on what's going on. So what we can see is, if we start by looking at the crack depth per cycle, so that plot on the left, we've got three tests: notch 1, notch 2, and notch 3. So notch 2 and notch 3 are a longer dwell again than notch 1. So notch 2 and notch 3 have more corrosion going on per cycle. And again, we can see that reflected in the fact that they take fewer number of cycles to fail than notch 1. So more corrosion, fewer number of cycles to fail. Again, that same story coming through. We can also see though that we get these crack jumps occurring as we resalt the specimen. So the crosses there on those curves represent the points at which we've resalted the test. So as our corrosive species or deposit is used up, it evaporates, or it's becoming used in the corrosion process, we have to kind of replenish that. So we can see how the crack jumps and interacts with those resalting processes. If we have a look at how this works out on a time basis rather than a cycle basis, we can see the story's a little less clear. So notch 3 and notch 2 again have some fairly big jumps early on. We've got more stress corrosion cracking going on, but they've not increased at a higher rate because there's less fatigue dominance going on as the notch 1 specimen. So there's no clear correlation in terms of time to failure in this case, because I think the mechanism is a bit more complicated than the SN curve sort of depicts. If we move on to have a quick look at the fracture faces of those kind of specimens, we see lots of environmental markings and things going on as well, which also represent those kind of start-stop type behaviour of the crack propagation mechanism. I think again it's fairly complicated. We've got multiple cracks interacting with each other and things, but it's sort of useful to note that start-stop behaviour is sort of represented on the fracture face as well. So I think quite interestingly, if we start to look at corrosion and fatigue interactions on a Paris curve, we can understand a bit more what's going on. So I've included here on the left a Paris curve. If you're not familiar with it, I'll just quickly run over what Paris curve is. So we've got stress intensity factor on the x-axis. So that's measured in megapascals root meter. So it's a kind of stress geometrical parameter, and it corresponds to crack depth. So as our crack depth increases, our stress intensity factor typically increases as well. On the y-axis, we've got the crack growth rate, so dA over dN, where dA is changing crack length over dN is change in cycles. And what we see for typical fatigue, if we look at the red line, is we see initiation, so a rapid increase corresponding between stress intensity or rapid increase between the relationship between stress intensity factor and crack growth rate, and then that levels off, so we get this flat line on the log-log plot, which represents a Paris curve, and we've got a constant and an exponent to help us or to model that. So that's our kind of typical fatigue area, and we'll use those constants quite frequently to model fatigue. And then again, just towards the end, we'll see crack growth deviate from that Paris line again. So really, that bit in the middle, that C straight line, is our Paris growth, and that's when we know that our crack growth is fairly in line with a typical fatigue dominated crack growth. So if we have a look then at our 3 results plotted on the Paris curve, so the plot on the right here, what we see if we start looking at notched 1, so to the left of what I put in there is a threshold line, we see there's very little or no relationship really between stress intensity factor and DADN early on in the crack growth. Our crack propagation is driven really more by time dependent or corrosion driven factors rather than stress intensity factor. However, there becomes a point at the crack depth at which the crack then starts to grow more in line with fatigue. So when we look to the right of that threshold line for the notch 1 specimen, we actually start to get that straight line. So that Paris curve is starting to come through there. So we can sort of hypothesize that at that point fatigue has become the dominant factor. So to the left we've got stress corrosion cracking or time dependent mechanisms dominating our crack growth, and to the right we've got more fatigue coming into play. And I guess what's quite interesting is to compare the notch 1 to the notch 3, notch 2 and notch 3 specimens. So notch 2 and notch 3 are a longer dwell, so there's more corrosion going on, but we actually see the crack depth at which they start to behave more like fatigue, or they start to correspond to fatigue crack growth is higher. So that's telling us that corrosion in this case is actually suppressing fatigue. And again, we can hypothesize that that's could be due to a couple of reasons. So there's crack closure which can occur. So that's where your corrosion product actually wedges open your crack, effectively reducing your delta K, so your stress intensity factor range, because there's less crack opening and closure occurring. Or there's also crack tip blunting effects, which can also happen. But I guess this relationship of corrosion suppressing fatigue growth is perhaps slightly counterintuitive. I guess it's important to sort of highlight the fact that suppressing fatigue growth is certainly not suppressing the corrosion or stress corrosion cracking driven propagation going on earlier. I suppose as well interesting to note is that this is also quite similar to the behaviour of single crystal superalloys between air and vacuum. So we will actually see that crack fatigue propagation in single crystal alloys in air is slightly worse, or there's less fatigue crack propagation in air than there is in vacuum at high temperatures. So I guess there's some comparisons that can be made there, and I suppose we see those effects more maybe in single crystal alloys because we don't have grain boundary oxidation going on and other forms of crack propagation occurring. So I was going to lastly talk a little bit then about why does all of this happen? What is a mechanism behind it? So I was going to start off here. I've got a few SEM images of a statically loaded specimen again, so no fatigue in these last few slides that I'm going to present here. So what we can see again, and it echoes what I was talking about earlier, we can see the crack propagating on Q planes, so 100, 001 and 010, and we can see corrosion interacting or preferentially attacking the gamma prime. And image C there is showing what looks to be an early corrosion pit with again corrosion interacting preferentially with the gamma prime. Image D is actually showing slightly the opposite. So that's a corrosion pit, but it was taken on a compression side. But we can actually see that in that case, the corrosion is interacting more with the gamma matrix, potentially suggesting that there's some stress factors in this preferential attack, but also just highlighting the complexity of this corrosion mechanism as well. And certainly that echoes a lot of what I've seen. You can convince yourself of one thing, and then several weeks later you see something that's just completely the opposite. Really throws a spanner in the works. So looking then at some higher mag images, so these are transmission electron microscope images of the crack tip. What we can see is the crack cutting through and propagating through the gamma prime, quite interestingly, because again, just to highlight, those gamma prime phases are strengthening, so they're quite a lot stronger than the gamma. We can also see dislocations, so stacking faults on the octahedral planes, so 1-1-1 stacking faults ahead of the crack tip. Again, that's not unexpected at these temperatures. We would expect to see slip occurring on those planes, but interestingly, the crack doesn't really appear to interact with them. So I think if this mechanism was fatigue driven or if plasticity was particularly important, we perhaps see the crack interacting and propagating a little bit more on those planes than we do. But we don't. It seems to just carry straight on ahead on the cube planes. So some EDX then, just to look at what's going on the crack tip here. And again, I've just taken a little snapshot. I've looked at quite a few of these. But what we can see is, firstly, there's no convincing evidence of diffusion or absorption of corrosive species ahead of the crack tip. It all appears to be happening at the crack tip. There's not much going into the material. Certainly not a lot of evidence I've seen of that. We do see presence of electrolytes at the crack tip. So you can see we've got sodium there right down at the crack, so top left. If we have a look along, we've got our alloying elements, and you can see how they segregate between the gamma and the gamma prime. Quite interesting. Nothing too controversial there other than the tungsten in orange, which we found in the gamma prime, and I think that's slightly debated, but certainly we see it. We've seen it more in the gamma prime. We've also got oxidation going on right down the crack. So in green, the bottom left, we can see how oxidation is happening right down at the crack. So the proposed kind of mechanism I've come up with then is sort of fairly similar to stress corrosion cracking. It certainly has a few analogies which can be made to stress corrosion cracking, aqueous stress corrosion cracking at lower temperatures, but I suppose this is a high temperature mechanism. And while stress corrosion cracking I think is a bit better understood, I think we're still really trying to understand in some detail the chemistry of what's going on here. So this is a simplistic view of my hypothesis. But what we see is typical hot corrosion type features. So we've got a nickel cobalt oxide. Below that, we've got dissolved oxides, and then below that, we see kind of an electrolyte. And I've put sodium sulfate there, but I think again there's a number of compositions that electrolyte could be. So we then see formation of a pit or a crack, kind of locally. Again, I don't think there's any definitive way. I don't think it's a pit and then a crack or a crack and a pit. I think it kind of probably just depends a lot of the time. And if we move down then to image B, in terms of how this sort of electrochemical circuit gets set up in the crack. So we see our electrolytes wicking down the crack, and we see oxidation happening kind of around the crack tip, and we'll see a localized anodic region somewhere near or at the crack tip, and really that's where we've got sort of acidic conditions and dissolution of the oxide and the substrate going on. And I think it's that localized nature really that drives this mechanism. We don't see broad fronted attacks, we see very localized attacks which cause, colonies of cracks. And then the image on the right, I suppose, is me trying to theorize as to why we see corrosion cracks or corrosion driven cracks propagating on orthogonal planes or the cube planes, rather than where we would typically see them on the slip planes, the 1-1-1 octahedral planes. And I think that's because if you take a point at the crack tip where you have a localized anodic region and you grow that out, you can see that the gamma prime features, which is kind of, or the gamma prime phase, which is kind of preferentially interact with from that point, are all kind of orthogonally located from that crack tip. So that's kind of my theory as to one of the reasons why we see this preferential orthogonal growth and propagation occurring. So I think with that, hopefully I've not bored you too much. But yeah, thank you very much for listening, and we welcome any questions.
Okay, so thank you very much for that, Laurie. A really fascinating walkthrough. Some of the detail there on what we're doing in terms of physics modelling for corrosion fatigue. There's a couple of questions come in. Actually, there's one particular question that's come in about connection problems, and I don't know if that's been a very localized issue or if that was something that a number of people have seen there. All I can do really is apologise for that at the moment. Obviously, the IMechE, we'll get in touch with the IMechE and talk to them and find out whether or not there is an issue with the platform, or whether or not it's just a localized issue with that particular individual. But like I say, if there has been an issue for you, then we're very sorry about it. And I guess it's obviously IMechE to investigate what's going on with this platform. I think it's WorkCast is the platform that we're using today. So moving on from that, we have got a bit of time for some questions, and a number of questions have been coming in. I've been sifting through them a little bit to try and get some sensible ones out. But actually, there's a load that have just come in the last couple of minutes. So I'm going to kick off with a question directed to you, Laurie, and then I'll have a look through the inbox and see if there's any other interesting stuff that's come in. So the first question from Arun. Can't work out where you're from, Arun. You're an engineering manager. The email address is msn.com. The question is, how do you assess standstill corrosion in a gas turbine? It's a very good question. So, Laurie, I don't know if you've got any thoughts on that.
Yeah, thanks, John. I'm just standstill corrosion isn't a term I'm necessarily familiar with, but I can sort of imagine you're referring to corrosion kind of, not during operation. I don't know what your view is on that, John.
Yeah, that's exactly what it is. So obviously,
yeah.
if you leave a machine standing still, especially near a marine environment, how do you protect that from corrosion? And the answer is you protect it from corrosion by blocking the airways and keeping it warm and keeping it ventilated and keeping it dry. That's not something that we particularly cover directly in what we're doing, but that's not to say that we can't develop corrosion models that are appropriate, especially for the compressor and those sorts of components. The answer is we can develop those models and we can put that physics into these models. But primarily, what we're doing is looking at what's happening during the operation and whether or not you can get more life or get more use from your engine rather than get more standstill time out of your engine. I think is the short answer. But the long answer is we can develop those methods if you need us to. Okay. I don't know if you've got anything to add to that, Laurie. You might tell me we can't do that.
No, I think you're right, and that was my kind of understanding as well. I guess it's standstill corrosion is perhaps a bit more of an issue now. There's lots of assets not being used due to COVID, so yeah, probably quite relevant question.
Okay, all right. So I'll tell you, there's a number of questions that are coming through on sort of the general, and there's actually one or two that's been directed to me. So I'm going to start answering some of those questions. If you want to look through the inbox and see if there's anything that you want to answer there, Laurie, then start having a look at that, and I'll hand over to you in a minute. Yeah.
Cheers. Yeah.
Okay. So there's one here from James Maddock at Rolls-Royce, directed to me. You mentioned the use of predictive physics-based approach to potentially take credit for part power operation to extend the life of assets. The question is, do you use this for safety critical applications? Is your tool set qualified for this? I guess the question from Rolls-Royce, a safety critical operation would be potentially an aero engine, and the answer is we haven't developed it for Rolls-Royce aero engines, but we do believe the physics is sound, and we do believe that we can certainly support you in your operations. And I think actually some of our engineers are supporting your teams in terms of physics-based assessments of your components. But primarily the work that we've done is on the industrial gas turbine side, and that's anything from a 10-ish megawatt machine to a full-size frame engines which are operating in power stations around UK and actually Europe. And there's something there about the tool set. Yeah, we have methods that we develop, but we don't have a set of software that we just license that you can plug your engine into. We develop bespoke solutions, and those solutions can be for the OEM who runs a fleet of 15,000 engines, or it can be a bespoke solution for a particular power station that has a particular type of gas turbine, and we'll develop those methods either way. And they have been validated. We work with the power station, we work with the insurer, and we work with the OEM to see the best way of managing that plant. And quite often we're very successful in getting more hours of operation out of that plant before the maintenance window is due, if you like. Hopefully that answers your question, James. There's a couple of questions come in on the uncertainty modelling and the Bayesian approaches, if you like. One of them, oh gosh, something's happened to the order of the questions while I've been talking there. One of them comes from Ian McAfee. You've asked how big a problem is uncertainty in measurement, drift characteristics of the thermocouples, what are the effects of this uncertainty? And then Cam, I think you're in Hong Kong, Cam, you've asked, may I know more about risk-based decision tool? I think there's some more come in whilst I've been talking and whilst Laurie was talking there on uncertainty. It's quite an interesting area. I think you know what, the short answer is I think we need to do a session. I'm gonna try and organise a session with the IMechE and do another one of these webinars where we can talk about the risk-based methods that we've been using. Getting into the detail, there is a massive problem with uncertainty on the measurement side. You know, what happens if a thermocouple fails whilst you're sat there monitoring it? How do the algorithms deal with that? Yes, there's drift on thermocouples, and yes, there is inaccuracy in the measurement. And, you know, if you just think of a basic sort of rule of thumb type thing, then you know a 10-degree difference in temperature can give you the order of magnitude of about 50% difference on a creep life calculation. So you know that level of uncertainty on the measurement can lead to quite a lot of uncertainty in terms of your prediction of creep damage and therefore the amount of damage that you've actually done to your engine. And a simple way of sort of adding all of those uncertainties up will generally, if you just add those uncertainties on top of each other, you will end up in a position where you've got so much uncertainty that you've got absolutely no clear view on how much damage you are predicting with your engine. And so this is where the probabilistic methods that we've been using on nuclear power stations and actually adding up those uncertainties in the correct way to give a realistic view of your uncertainty. That's where the value really comes into this. And I think we do need to put a presentation together on how we're doing that because it's a little bit difficult for me to answer in this session. But I'm going to make that happen. I'm going to make that happen. We are going to do a session on that, and hopefully you guys can watch that and learn more about how we do that. In the meantime, if you want to get in touch, I can put you in touch with those teams and they can talk about that more. Hopefully that's enough on that. Pradeep, where are you from? You're from the Ministry of Defence Standards Engineering. That's interesting. So you asked an interesting question. Do you use machine learning and artificial intelligence in your data analysis models? Not in this instance. We do have that capability within the company, and we can use that capability in terms of trending what's happening to fleet of engine and that type of stuff. What we're talking about here today is really about our physics-based approach to understanding what's going on with the damage accumulation within the engine. And there's a time and a place for those sorts of things. So if you think about highly complex systems like the hot gas path within a gas turbine, it's very, very physics driven. Machine learning algorithms are not particularly suited for that type of stuff. If you think about a situation like rotor dynamics, you can predominantly, you're looking at an uncertainty model. There's so much uncertainty in what's going on with that vibration monitoring that the physics model gets a little bit swamped from my experience. I'm sure there's people that would disagree with me on that, but and I think that's kind of, there are scenarios like that where machine learning and artificial intelligence can actually be a lot more helpful than the physics-based approaches. That would be my answer. I don't know if you've got any further views on that, Laurie.
Yeah, I'd agree with what you've said. I think as well, though, with the physics models, we'll understand them and generate them from testing, like I've shown, or analysis, and get the model. But often we'll then fit it to large data. So it's not a typical machine learning as such, but it is kind of an automated fitting process. Often, I think, where you have a lot of data and you have a model, but you need to look at how that, what your constants and parameters are for your model, considering your data. So I think that's kind of machine learning in my eyes, or my mind. It's more fitting though, I suppose.
Yeah. Okay. I'm sure that our answers, the question and our answers, has probably opened up a whole area of debate there. But actually, looking at the clock, we're pretty much out of time. I don't know if you've been looking through the inbox and whether or not you've spotted any more questions that have come in, and if you want to answer any of them before we close out.
Yeah, I think you're right. We're running a bit low on time out there. There were a couple. I'm just trying to see.
Yeah.
There was one by Alfred on single crystal blades being good for high temperature, but not for H2S and CO2 environments. And I think I made mention to this, that as we try to sort of push the operational temperatures of these, we turn more and more to single crystal blades for their creep properties, I think in particular. But often, the detriment of the corrosion and oxidation properties. So I think we can obviously look to different materials, but I guess coatings as well is another area, and several surface treatments offer possible solutions that you can look to. But again, it's obviously all quite sort of complex stuff and needs individual consideration, I think, perhaps a lot of the time.
Yeah, I agree with that, actually. So that's a really good point by Alfred. Certainly the newer generation of single crystals, which have got quite low chrome contents, they tend to suffer more in these types of environments than the earlier generation. And actually, we funded a PhD at Cambridge University to just look at that problem in particular, and we never got to the techno-economic assessment, for want of a better word, which sort of tries to weigh up the argument of is it better to put an expensive coating on, or is it better just to use a sort of an earlier generation of single crystal which has got higher chrome content. It's an interesting subject area, and I've never got that deep in it, but it's a really good point by Alfred, I think.
Yeah, definitely.
Yeah. Okay, so I think we're running over the clock, and people have probably got meetings to get to on Teams and that type of stuff. So I think we're going to pull stumps there, unless there's any other burning questions that you want to answer, Laurie.
No, I'm happy with that. Thanks, John.
All right. Well, then I guess it's time just to say thank you very much to everyone who's made it this far, and I hope you found it interesting. And like I say, we'll try and get some more sessions organised around the probabilistics and that type of stuff, and hopefully speak to you again soon. Okay. Goodbye.